and I come from the University of Geneva, and today I will talk about some past work and some current work on the provision of cloud services for big data management and analytics. So cloud information systems are all about providing virtualization of distributed and utility computing as services on infrastructures that are large, elastic, and are most of all adhere to business policies that are bound to technical solutions. So offering data management as a service has to do with the following problem. Without cloud data services, we have people, users asking for the data, wanting to query the data that reside most probably in distributed databases. So without cloud data services, we have other people and companies developing data management applications, and usually these applications come with errors, incompleteness, inefficiency, because the ones that develop them may not be as skilled as they're needed to be. They take a lot of time to be developed, so if they're not good, we have lost time and money. They are heterogeneous, which means that people that want to ask the same things from the data, they end up with different solutions. And even if one solution is good, this experience is never transmitted from user to user. So we cannot use the experience. With cloud data services, we can solve these problems because the cloud data provider, data service provider, can provide solutions, data management applications actually, that are efficient, they are systematic, optimized for many users, they are complete, and most of all, they can be reused. Big data have to do, usually, big data management has to do most of all with the management of big analytical data. And a very nice use case for us, so the people that work on data management, is the case of scientific data. Why? Because scientific data, beyond their size, they come in many diverse formats. They have very complex dependencies, and they are dispersed in many locations. So this leads to very intensive querying. So we have short-running queries, but also long-running queries from the data, and systematic querying, many users asking for this data. A cloud data service provider that wants to service such data has a cost, and then the cost comes from mostly from operating the infrastructure and the administration cost. Breaking down this cost, the cost derives from the data storage design, which means that we have to take decisions on how to store the data in column stores, row stores, or in combinations, and how to replicate them. Query optimization, which means to create and maintain data structures in order to accelerate query execution. So query execution without data structures is very slow. Data structures are actually additional data built from the original data, like indexes, views, and partitions, and they are used in planning the execution in order to accelerate, make it faster. And finally, the cost comes from query execution itself, which means creating alternative query plans for execution and selecting a plan for actual execution and parallelizing the execution on the cloud infrastructure. This is translated to an economic burden that is put on the cloud data service provider, and therefore such a provider, in order to operate and be at least economically viable, it has a requirement for a cloud economy. So the inputs to a cloud data service provider are the data requests, what the users want from the data, the data updates, so how the data changes in time, the cost of operating the infrastructure, and what are the user budgets, preferences of the users in terms mostly of money, but also in terms of time for query execution. And taking this input, the output of the cloud data service provider should be decisions on how to service the data. This output is actually the answer to 4 questions. What is the cost of any service that can be provided? How should we invest in services? So what services should we, how we should execute the queries, and what data structures should we provide? What is the depreciation of services? So from the time point when we offer a service, how much the service can be of use to users, and if we can make some profit. To solve this, so the challenge here is to actually do efficient data management as we have been doing in the past 30 years or 40 years, but also perform it in a manner that is cost aware of the monetary cost. To solve these matters, we have proposed a framework that is economy aware. So it's a framework that decides what are the services to be provided on a cloud infrastructure in a manner that is aware of the economy of the cloud, that the cloud has an account and this account pays for these services. This layer gives the answer to the previous questions, which is actually the service cost, estimation of the service cost, the service investment, in which services should we invest, the depreciation of services, and how we can make some profit. So in the first part of the talk, I will give some views on this work, on the framework, and in the second part of the work, the talk, I will give a view of some current work. Now, how does the cloud operate? We have the users from one side that communicate with a cloud provider through an interface, and the cloud provider has a cloud database management system. This is some data DBMS that is installed on the cloud infrastructure. This is a whole other topic. What is this cloud DBMS? And usually this cloud DBMS has access to multi-cores and many CPUs, to a distributed file system, and the data may reside either in the cloud or in external databases. The user gives as an input a SQL query, and a budget, which means how much money I'm willing to spend on this query. Actually, this can be, in general, user preferences. And the cloud takes decisions, and the decision is how should I execute this query, and if I should build data structures to accelerate query execution of similar queries in the future. To take these decisions, the cloud follows specific policies, and these are, of course, the following. First is individual user satisfaction. So any user preferences should be respected, which means that if a user wants fast execution, she should get fast, cheap, she should get cheap. The users should never be overcharged for the data services they receive, and user budget constraints, of course, if they're there, they have to be respected. The second policy is related to data service improvement, which means to be able to offer more appropriate, and this means usually better and broader services, and offer the same services at a lower price with time. And the third policy is related to profitability, since we may be talking for a commercial cloud provider. And this means that we want to set in an optimal way the prices of the services, as well as schedule in an optimal way the availability of the services. We have proposed 4 modules. So the framework includes 4 modules to realize these cloud policies. And these are the following. The first one is a cost model that estimates as accurately as possible what is the cost of any services that can be provided. The second is a regret scheme, which is actually the investment scheme for new services. The third one is a prediction model that estimates how long data structures can be used to queries. And the final one is a pricing scheme. So in the following, I will give some views on the first 3 modules, but not on the last. If there are questions, I can give more details on the last one later. So any structure in a query plan induces a cost. So a SQL query enters the cloud, and this is translated to a query plan, an execution plan on the cloud database management system. This means that it goes through a cost model, and the cost model estimates the execution cost, that is the cost of actually putting the query to run on the cloud infrastructure, and some cost that is derived from using structures that are already built in the database management system. And this is the query cost. Now, the cost functionality overall is as follows. It takes as an input either a query plan or a candidate data structure, and this can be an index, a view, or a partition. And for the query plan, it breaks it down to basic data operations like scan, joins, and selects, for which we have estimations on how much they cost to be executed, to be performed, realized in the infrastructure. And for the candidate data structure, it estimates what part of the infrastructure it uses, how many CPU cycles, what part of the input are, how many input-output operators, what part of the bandwidth, and how much storage. And for the query plan, it gives us an output, the execution cost. And for the candidate data structure, it gives us an output, how much it costs to build the structure in the cloud DBMS, and how much it costs to maintain it, store it in the cloud thereafter. So a SQL query enters the cloud, and it's actually received by the cloud DBMS. The cloud DBMS must have an optimizer. If it's MySQL, it will have the optimizer of MySQL. If it's HBase, it will have some other optimizer. Now, the optimizer takes into account if there are available data structures to be used in query execution, or if we can build new possible data structures. Taking this into account, it gives us an output, the available and possible query plans. So available query plans are those that can be executed right away because they use only structures that are already realized. And possible query plans are what-if query plans, as we call them in data management, which means that they use structures that are not yet there, but we have estimations for them, cost estimations, cost and time estimations. This goes through the cost model, and the cost model gives us an output execution cost. So for every query plan, now we have a set of query plans that are proposed by the optimizer, and for every plan, we have a pair of two values. The one is the execution cost, and the other one is the execution time. So we need to optimize on both axes. We plan the values on both axes, and we take the skyline of these values, which means the subsets that are best, that includes the plans that are best for both axes. Now, we can use this subset to select the plan for query execution, but before we do that, we need to take into account if there are any user preferences. And the user may prefer to have cheap execution. I don't want to spend a lot of money, but I don't care about time, or fast execution, or she may give a specific budget function, which means that if you run my query really fast, which means 1 millisecond, I'm willing to spend up to $10. After that, I'm willing to spend only $1 until, I don't know, 1 second, and after that, I'm not willing to spend anything. So we take a subset of the skyline, a subset of the subset, which we call the valid region of plans. It's the subset of query plans that are best for both axes, cost and time, but also adhere to the user preferences. From this subset, from the valid region of plans, we can select a plan for execution. And we can also accumulate this data management experience in order to decide on our investment scheme. So how do we do this with an example? Let us assume that this is a valid region of plans, and we have available plans in these region and possible plans. We have 3 available plans and 2 possible plans. If the user wants fast execution, we will select the fastest available plan, and we will regret for not being able to offer the even fastest possible plan. In the same way, if the user prefers cheap execution, we will execute the cheapest existing plan, available plan, and we will regret for not being able to offer the even cheaper possible plan. If the user gives a budget function, then we will execute the cheapest the plan that is closer to the budget, and it is available, and we will regret for the plans, it may be more than one, that is even closer. Now we have selected the plan for execution. We're actually executing the query, and we have collected some regret. This regret is quantified as the difference of the cost of the possible plan, the what-if plan, and the plan that has been actually selected. This value is normalized with the cost of the possible plan. So this regret shows us how much we have not done the optimal thing, let's say. We could do better in our selection, but we couldn't do better because some structures we wanted were not there. So what can we do with this regret in order to decide what structures to build? Let us assume that this is a query plan that is a possible one. So it includes one or more structures that are not yet built. Let us assume that the triangle, which is an index, is an index that has not been built, and we want to decide to accumulate the data management experience to see if we can and should build it at some point into the cloud DBMS in order to offer it to query plans. So we have some regret for this plan, and the regret is disseminated in an equal way to the structures in the plan. Now, if this index is very popular among what-if plans, then this means that we will accumulate regret for these plans, and the regret for this index will increase with time. If it's very popular, it will increase, or not only very popular, but also the regret for the plans is very big. So very important structure. This regret will increase fast, and at some point it will be very comparable to the building cost of the structure. So when the regret that we have accumulated, which is actually money, is comparable to the building cost of the structure, then the cloud DBMS decides to spend money from the cloud account and build the structure, offer it to new query plans. So we have taken imminent data management decisions, and we have decided how to invest in new data structures. Now, these new data structures have incurred a cost, and this cost should be amortized to users that will use this service. How can we amortize the cost? Now, the query plan has a cost, and the cost, as we said, comes from using structures. So using structure S1, S2, S3, and 4, and the actual execution cost. So a query plan should not pay for the whole amount of the structure, because many query plans benefit from this. But how much should we pay? How big these ends should be? Should they be small or big? Now, the observation is that it is possible, but not probable, to have plan executed in time and using S that is random. The probability of using S as it is random. But this is not, it is possible but not probable. So the probable thing is to have a decreasing probability. Why? Because data management has shown in the many years of experience that we have query similarity that shows temporal locality. So queries that ask for similar data or ask in a similar way for data come close in time. So we have locality, therefore if a plan uses a structure, then the probability that other plans will use the structure is bigger if these plans are executed close in time. Also, why do we care about the building cost and not the maintenance cost? Because the maintenance cost is 7 times smaller than the building cost. So if we amortize the building cost, we're covered actually. So, okay. Because the probability decreases, this means that we don't want to have long amortizations, because we'll run a risk of having the total cost non-amortized, because query plans will not use the structure anymore. But should we make them short anyway? Now, the cost of the query plan decreases as n increases, but we don't want n to be very big. But it increases if n decreases, of course. We have an inverse proportional relation here. So this means that if we make amortization very small, very short, we will reduce the risk of non-amortization because of uselessness, let's say, of the structure. But we will end up with query plans that are very expensive, and we don't want that because this would most probably be out of user budgets. Users will not want to pay for this. This will not be competitive in the market. So therefore, we have developed a prediction model that is based on survivability theory. And I will show the guidelines for developing the model. Now the question is how much a structure can survive in the cloud DBMS. The word involved is survive, so the answer here is as long as it doesn't fail. So survivability is equal to non-failure. Failure is a necessity for a structure to be updated or discarded. So we have 4 types of events: storage limit, obsoleteness, uselessness, and redundancy that create instances of failures. And these events can happen in time, in various times, after the building time of the structure, with random order and repeatedness. So each one of them is a failure instance. So we have to base the survivability on the probability that structures will fail because of these events. Now the question is how much can a structure survive? And the answer to the word much is a number of plans in a time period. This means that query plans that arrive after the building time of the structure can use or cannot use the structure S. So we need to be able to provide, to predict also that beyond failures. Now, having these two issues in mind, the prediction model is based on 2 novel notions. The usefulness of a structure, which is actually the probability that S is used on the grounds that a plan is executed, This means that if we have plans arriving and being estimated that they can use or not the structure, we discard the time between the plans. So we say that this time has not happened. We don't care about the time between plans. And the second notion is the stability of the structure S, which is the probability that data does not change. Does not change, so we don't have failures. Now, these are the guidelines on which the prediction model is developed, and I won't present the actual prediction model, but we can discuss it later on if you're more interested. The real thing is this framework, we have realized this framework as a system which is called COCUS, and COCUS comes from the phrase self-configured cost-based query services in the cloud. COCUS realizes this cost-aware execution, query execution that I have described. It adaptively charges queries and adaptively makes the optimization of queries, and it abstracts the cloud economy. It has a module that is called Cloud Economy Module, and decides how to execute a query, what plan to select, which plans are what-if plans, and what are the what-if structures. It has a module that realizes the cost model, and a module that realizes the prediction model, and a module that regresses real data on the prediction model. It communicates with the cloud DBMS, and the cloud DBMS for us is either a relational database management system. In the demo, it was MySQL or HBase, so NoSQL data. The user can select if the cloud is a private cloud or a public cloud provider, if the data are relational or HBase data, and it has to select one of the three policies as a primary policy. So individual user satisfaction, quality, and then what we show is that even if the user prioritizes one policy, then the system actually starts by optimizing using this policy, but it actually converges into optimizing all the policies. Now, the second part of the talk, I will talk about some ongoing work, which is on the cloud DBMS. So the vision is to offer cloud services for big data, and in a ladder that has to do with data per user, we have three types of cloud environments. The first step of the ladder is about personal and community data. So here we can have clouds that have maybe small data, but thousands or millions of users. So having federations of clouds that maybe may comprise also private clusters in the public cloud providers, but they mostly comprise individual devices. So for such clouds, the vision is to offer services that make it easy to use the infrastructure, make it easy to access the data from all the devices and exchange data as well as communicate, and even allow for some profit, allow to rent your devices in order to make profit. In the second step of the ladder, we have more data per users, but smaller number of users. And here we have the small and medium enterprises. So here we have the goals, the objectives that are well known for cloud services. So lower upfront costs in order to make a new enterprise, enable the enterprise to go faster into the market, running a reduced financial risk, allowing for non-over provisioning for data for administration, and running a reduced cost from downtime. And on the third step of the ladder, we have big data analytics. Here, the scientific data that I have described earlier belong to this part. And the goal here is a mixture of the goals of the two previous categories. So we want to offer ease of use of the infrastructure, data exchange and communication, solving the heterogeneity problems, but we also want to offer no over-provisioning, no cost for administration, and most of all, efficient complex analysis of the data. So if we can do that, we can actually boost both business and research. In this vision, a cloud-based system for big data has three layers: the bottom layer of cloud DBMS, the middle layer of the services, and the top layer of economy. The work that I have described, the past work is on the top two layers of economy and services, but not on the cloud DBMS. Now this work is on the cloud DBMS, which means that here we care about the storage architecture, how to share the caches and allocate the processes, and also how to place the data in the cloud infrastructure, which means decide on the replication schemes and the storage. It has also, this work is also a bit on the service layer, because the previous work was on managing only individual queries. Here we also want to manage workflows or groups of queries. Now the project that wants to realize all this is called ASAP, and ASAP comes from the phrase Adaptive Scalable Analytics Platform. This is a new European project that that started in March 2014. And our proposal to big data analytics is that we need a system that is fully automated and highly customizable in order to be able to develop and execute arbitrary data analytics queries. Now, it has three objectives. The first one is to offer a programming model in order to develop complex and irregular data center queries and application. The second one is offering a modeling framework that will do actually optimization, considering the type, size, and location of the data, and the type of computation, the resources, and the runtime machines. And the third one is an adaptation methodology that will be able to calibrate queries and workflows on the fly and see and integrate intermediate results. So we'll talk a bit more about the last part, in which I'm more involved. So online adaptation of analytical queries is related to management of a workflow. So formalization of tasks, abstract tasks, determination of dependencies between the tasks for the data, and scheduling of these tasks. The second is a deployment of the data processing. So how we can integrate the data, when should we integrate the data, and how we can do multitasking optimization by mining commonalities. The third is recalibration, online calibration processing, so adding more workflows into the system and re-optimizing every time, and also adding or removing deadlines and milestones. So a query in this system can be formed as tasks that relate to many different types of data and, of course, many different types of runtime machines. So here we can have a query that asks for data that are graph, file, or stored in a DBMS, in relational DBMS. So we need three types of engines, one for each type of the data. These will be able to access the respective data, bring them back, process them, and maybe move them to other types of formats. In order to do that, we need to have indexing schemes, execution planning that provides for many runtime machines, a specific language, storage, and prefetching schemes. And I will talk a bit more about the language. Now, what is a workflow? A workflow is a group of queries that can be scheduled in many, that can be ordered in many specific ways. So here we can have a query group that includes three individual queries, and then after the execution of this group, we would like to execute another query group that includes the execution in a specific order of two other queries. So this is a workflow. And such workflow of queries may also comprise algorithmic processing and also iteration. So we have a long-running query that queries data in partial orders, does some algorithm processing, and does that again from the beginning. So a workflow is that plus some metadata on deadlines, milestones, and limitations or restrictions or intermediate processing. So what we need is a language that can query, can create these queries and workflows. So we need a language that can access all these types of data, and it's like SQL, which means that we need operators that can be translated in many runtime machines, and especially for the relational mode. So a query and a workflow is created using this language, and it is translated to the actual language of every runtime machine, to a relational language, to a file language, or a graph. Now, this can be done either using a declarative language that is already there, or using stored procedures and processing strategies. Now, we can declare this workflow, and then before actually executing the workflow, we can analyze it and optimize it before actually this is being put into the system. What does this mean? Let us assume that we have a query group to be executed that includes two queries, query 1 and query 2. And these queries actually want to query data as shown. So query 1 wants to query HDF data. These are scientific data of hierarchical format, two resources of RDF data, and relational one, and a relational store. And the second query wants to query the same HDF and RDF data and some XML data. So what we can do is that we can regroup them in a way that the stores are queried together from the two queries. So we have another group that includes partial parts of query 1 and query 2. It includes querying the scientific data and one RDF store, and the remainings of the two queries. So query 1 asking for relational and some other RDF data, and query 2 asking for XML data. So we do this pre-optimization before putting this analyzed workflow into the system, plus some optimization on the relative schedule. So what the system will do is that we have two-stage optimization: workflow optimization and optimization of the system, which we call intelligent scheduling. So in order to do workflow optimization, the workflow layer asks for estimations about processing, data migration, and general costs. Getting this information from the system, it makes the analyzed and optimized workflow for cost estimation. It sends it to the system, and the intelligent scheduling part sends corrections. With the corrections, the workflow optimization layer re-optimizes it. And this is done in a feedback loop. It is done continuously. So we have feedback from layer 2 to 1, from the intelligent scheduling to 1, if the schedule deviates from the goal. And we have feedback from one workflow optimization to the second, when we have new workflows to be run, or new limitations on the deadlines and milestones. So to summarize, cloud data services are attractive, as we all know, and they are especially useful for the management of scientific and big data management in the cloud. Economy is very critical for the success of such a cloud data service provider, and we have proposed that in order to achieve this success, we need to estimate in an optimal way the service cost, reduce past experience, predict the service consumption, and of course price the services. Finally, a multi-aware data service environment needs a system that includes three layers: a cloud DBMS, a middle layer of managing the services, and a top layer of managing the economy. Thank you.
Very, very insightful talk. It was a lot of stuff. I'm very impressed. But my question is, have you considered NoSQL big data? Because they deals really differently. Because if you use Cassandra, things like that, they tend to look at the data and then break things down. So you may have a different cost model, because their rationale is that once the computation is done within seconds, because you have some algorithm to optimize it, the cost actually is lower. That's their version. So I wonder, will you actually consider using NoSQL data, because you are using the traditional type of data?
Thank you. System actually uses also NoSQL data.
Things like Cassandra.
We didn't use Cassandra. We used HBase.
Oh.
So, but we actually used yes. HBase, yes, yeah.
For the experimental result?
No, because these are results from the actual system that is called Cocus, and we have many graphs showing the results, but they're not. The graphs are not published. The system is there, but the graphs are not published.
HBase tend to use map, then reduce, and yes, probably they go multiple map, multiple reduce. Yes. So this is what they do with data, and then some people they map several times and then they reduce several times. In a way, you optimize. So you don't do it like, I think your stuff is like do it once, do it another, but what they do is all together and then do it all together.
No. For the work that proposes the framework, how the DBMS works what does optimize is not a problem. We just need cost estimation. If this cost estimation is for running one map or one reduce or many map and many reduces, it's the same thing for us. We will the algorithms will decide for the individual mappers or reducers or for the set of them, depending on where the estimations refer to. Yeah.
I have a small question about just provider, actual cloud providers. Did you have an opportunity to talk with them and understand how this issue of building an intermediate structure to minimize the costs over time? Do they do that actually?
So this work started after a conversation that we had with Amazon people, but it was a long time ago. It was 4 years ago, and at that time they told us that they don't have any scheme to actually decide how to invest. How to invest? Okay, you can explain.
In the structure, how to invest in building the structure.
Yes, actually they didn't do that at the time. They didn't offer data management, but they didn't do that even for resources, for like investing in resources. So how do you invest in it? How do you say that I offer this amount of resources? You see, and they told us actually that what they do is that twice a year they sit around the table. They have all these graphs about how it went throughout the year, and they decided, but not based on an algorithm, but based on experience, on management experience. So the economy of deciding how to invest on resources was not related to how you operate the resources, how you provide the resources. You see? So the inspiration comes from there, that these two things, these two types of decisions, groups of decisions, should be connected. That was the inspiration.
Okay, and this notion of here you build the investment is building the index, for instance, an index structure. But when you speak about about resources, you speak about like buying servers or buying more from the provider point of view.
Yes. So we in this work we made it in a very fine granularity. So how you actually and the resources for us were the data structures because we offer data services. It can be, the models are so generic that they can be actually applied to other types of resources. Of course, it's an R or an S, it doesn't matter what it is. Now, of course, we have not put in I haven't shown that. It's future work, we have not put in the models how to buy or maintain the infrastructure. It's only how to operate the infrastructure.
I have one question regarding amortization.
Yes.
You said that there is an interest of doing amortization in a very short period.
That we shouldn't do it in a very short period.
You shouldn't?
We shouldn't.
Okay, good.
We shouldn't do it in a very big period because then we will lose query locality. So eventually queries that will arrive for execution will not need this structure, or data will be updated. But we shouldn't make it very short because if we make it very short, for example, if we make it one, then only one query will pay for this structure. But the cost will be so big that the user, then you will actually again lose money because the user will not actually pay for this query plan. It will not be competitive. So you want something in the middle. That's why you need a prediction level.
Any other question?